Hi students, welcome back to the online lecture series on VLSI testing and design for testability. As you are already aware, we are covering the topic of Unit 5 in this online mode. So the Unit 5 title is Analog Testing. Let me recap you about the topics that we have covered so far. The first topic or the first lecture, it covers the introduction to analog testing and the basic characteristics of analog circuits and the differences between analog circuits and the digital circuits. The second lecture, it covers the topics of analog fault models. So in that lecture I gave details about what are the different types of analog models that are used or that are being used in the industry. So today we are going to cover the topics of analog circuit testing. So here we are going to cover four different subheadings. The first one is analog test approaches, second is analog test waveforms, third DC parametric testing, and at last the AC parameter testing. So let us go into the topic today. So in analog testing, so whenever you want to test a particular circuit, what is the normal procedure? So we have a device under test or a DUT for a particular DUT which is taken for consideration. A particular set of stimulus or input is given. So the input is already known parameter. So for a given for a given circuit and for a given set of stimulus, we get a response, and by comparing the response uh, with that of the ideal outputs, we can test the performance of the particular circuit. In analog testing, we are having two different types of testing methods. The first one is called specification oriented or spec oriented, and the second one is called waveform oriented. So let me explain each one separately. First one, specification oriented test. So what is a specification? So consider an example of an op amp. So for an op amp, we have a set of characteristics that is defined by the manufacturer itself. For example, here for the op amp which is under consideration here, OP777 or OP727, for this particular model of op amp, we have a set of parameters that is defined by the manufacturer. For the input characteristics, we have offset voltage, input bias current, input offset current, input voltage range, etc. And similarly, output characteristics, output voltage high, output voltage low, and the power rating, dynamic performance, which has slew rate and gain bandwidth details, along with the noise performance. These are the details that will be given by the manufacturer of any analog any device. So consider this: whenever you are taking a macro or a rudimentary model of IC, consider an op amp or IC 555 that you buy as a component from the market. So how will you test it? So you'll have your breadboard or a workstation or an electronic workstation. So if you have some particular number of sensitive devices, you can easily measure the various details as given in this data sheet, and you will cross verify that. So this is the same process that will be followed when you are following the specification oriented test. Here, what are the necessities, or what are the details that we can get from a spec oriented test? First thing, we can check whether all the specifications are being met by that particular circuit, and then this process is tedious and inflexible. So if you consider a specification oriented test, it is more or less similar to exhaustive testing in digital ICs. So in a digital IC, what is an exhaustive test? For a given circuit, you will consider all the possible inputs and you will check all those inputs. So that is exhaustive testing. So similarly here, for you will be considering the circuit, and that for the particular device under test you will measure all the input and output characteristics. So naturally this process is very much tedious, and it is also inflexible, because it has to, for each and every measurement you need a certain procedure which cannot be changed. So considering an operation amplifier given in the previous slide, these are the various parameters that we need to measure in specification oriented test. Next, what is a waveform oriented test? So waveform oriented test is different from a similar from the specification oriented test in a way. In waveform oriented test, we are mostly concerned about what is the response. In specification wave oriented test, we are more focused on the different specifications or the different working parameters of the IC. In waveform oriented test, we focus on what is the behavior of the particular circuit for a given input. Let me explain it further. So consider you are having this particular circuit. Okay, so before you go for fabricating an IC, you will naturally go through a process of simulation and verification in software, that is prefabrication. In prefabrication, for each submodule you will be having you would have simulated it for various parameters. For example, considering an op amp, naturally the fabrication would be performed after the simulating of all these parameters of DC bias, input offset, slew rate, damping factor, etc. So what we are going to do now is we are going to check the operation of the circuit physical hardware and compare it with that of the simulation. So what are the parameters we are going to check? So for a given waveform, we will be checking DC bias, input offset, slew rate, damping factor, overshoot damping factor, bandwidth, settling time, DC gain, etc. So all these parameters will be checked. So we will be giving a sample input, and for that particular sample input we will be gathering all these details, and all the test details will be compared with that of the simulated waveforms. So if the simulated one and the post fabrication testing that we are performing on the IC, if it correlates, then it defines that the circuit is okay and it is performing well. If not, we have to decide that there is some kind of fault in the circuit. So analog test comparisons. What is the comparison between these two types of test? When you consider a specification oriented test, we need more test runs and more time is required, because it is an exhaustive process. Second, we need accurate instruments that are maximum it is costlier, and we need a perfect environment in which we have to check these devices. And the specifications or the test readings from this particular test, these are guaranteed outputs. So when you do the specification oriented test, since it is more exhaustive, outcome of this test is there will be low defect level, that it is highly efficient in terms of detecting the defects. When you go for waveform oriented test, it needs less number of test runs, and equivalently the test time is also less. Next, it does not need a lot of instruments for testing. And next, the third is, this is not a very effective means of detecting the defects in an IC. It is less accurate. So next is analog test waveforms. This is the second topic that we are going to cover today. What is an analog test waveform? We have a lot of modules or a lot of different types of modules in analog circuits that we need to check. For each different type of circuits, we need a different manner of stimulating the particular circuit. Here this is you would have come across these types of waveforms already. We have the sine wave, square wave or the step signal, the ramp signal, triangular waveform, chip signal, arbitrary signals, and modulated signal. So why are we going for these different varieties of signals? Depending upon the type of module, we need to choose a particular way of stimulating or activating them. For example, the sine wave, it is suitable for local oscillators, etc. But if you go for a square wave, it is not suitable for such things. Okay, square wave will be more probably it will be suitable for say bistable multivibrators, etc. Okay, so these are the transient equations for each and each types of signals. For example, when you consider step signal, if, we apply it for voice voltage control oscillators, filters, etc. Similarly, for a step signal, it will be step change in voltage. It is easier to test for transient testing. If you change the frequency, it will be applied for PLL testing, and if you change the amplitude, it will be applied for AGC testing. And ramp signal, sawtooth wave generation, chip signal, etc. So the next topic is DC parameter testing and AC parametric testing. So what are the DC parameters and what are the AC parameters? So if you consider DC parameters, the rated output current, output loop gain, unity gain, overload recovery, input offset voltage, input noise, supply voltage sensitivity, maximum voltage between the inputs, temperature drift, rated output voltage, slewing rate, unity gain, small signal response, input bias current, input offset current, input impedance, common mode rejection, maximum common mode voltage. So these are the various parameters that we need to extract when performing DC parametric testing. So similarly, we use the open loop gain measurement. So as I told you before, this analog ICs are more complicated because of feedback signals. So when you want to remove the feedback, and you have to consider the circuit without any feedback first, so then only you can gather the open loop gain. So for that, this particular DC parameter testing is very important. Next, unity gain bandwidth measurement. This is used for measuring the bandwidth. Next, there is a common mode rejection ratio and power supply rejection ratio. So these particular details are considered for the DC parameter testing that I have shown in the example. These are all the parameters that I have considered for the example of testing an op-amp circuit. Okay, when consider I am having a VLSI IC. So in that IC, like I told in the previous video lecture, consider the example of a smartwatch. if you have a smartwatch, it detects your heartbeat. So before, when you want to measure any biological signals, you have a you have a separate setup. Okay, you have a preamplifier, and then you have a op amp, and then you have filters, and then you have ADC and ADC, and then sampling and hold, and then you have the processing where it will be converted from analog to digital. Okay, so in this setup, the op amp becomes a vital part. Okay, so I am considering an op amp for explaining the different types of DC parameter tests. Okay, next I'll moving over to the AC parametric testing. So what are the AC parameters that we are going to consider? The AC parameters are generally, it can be generally considered as gain, phase, distortion, signal rejection, and noise. So these are the five different tests that we have to perform on any analog circuit. Okay, so to perform this, we need a setup. So what is the setup? Here the CUT means the circuit under test. So for this circuit, we need to give a stimulus, and we have to record the response. Okay, so how will you give a stimulus to the circuit? So in a digital circuit, you will be having ATPG, automatic test pattern generator. Here you will be having arbitrary waveform generator. Okay, so what is the function of arbitrary waveform generator? It generates random inputs, random waveforms and apply it to the CUT, to the circuit under test. So what is digitizer? So digitizer, it generally consists of a sample and hold circuit. Okay, so this sample and hold circuit, and then it will be connected to a ADC, analog to digital converter. Okay, so what is the component that controls this test? We have a digital signal processor or a testing circuit. So this what is the purpose of this testing circuit? So it receives the response, and it generates a it receives the response from the circuit under test, and it also generates give the control signals for arbitrary waveform generator. What are the types of parameters that we need to measure? The first one is maximum output voltage or the maximum output amplitude. So it is more or less like peak to peak fluctuations in the output. Okay, if you are considering an amplifier, we have a particular limit beyond which the amplification cannot go, because it will damage the circuit. So to determine this, we need to use this maximum output amplitude. So we here, what is the process? We fix the input sine wave at 1 kilohertz, and the output waveform, we are taking the digitized output waveform, and the DSP is used to eliminate the distortion and noise, and we check the fundamental amplitude. Okay, so why are we considering the fundamental amplitude? Because if there is any mismatch between the source and the receiver, there will be a creation of harmonics. Okay, so only we are considering only the fundamental amplitudes here. Next we are going to consider the frequency response. Why are we considering the frequency response? From the basic amplifier up to the filters, etc., which is more important? The circuits, analog circuits, are frequency dependent. So frequency since you are having frequency dependent circuits, we need to take the frequency response. So almost all the analog circuits, they have a filter. So we are considering and we are considering the frequency response parameter, and we need to check the frequency response. Next, for frequency response, directly we can take the frequency response and we can go for the Bode plot. Okay, by plotting it we can get, by plotting this graph, what can we gather? We can gather the gain margin and phase margin of the particular circuit under test. Okay, so what are the other parameters that we can derive from this frequency response test? Here we can get the stop band, pass band, ripples, rejection ratio, etc. So these are the various parameters that we can derive from the frequency response details. Okay, so next, so why are we going for these things? As I told you before, in this graph, in the waveform test, I have already told you there are certain parameters that we need to consider. What are the parameters? We are having in C overshoot, damping factor and bandwidth. To get the actual bandwidth, we have to consider the overshoot and damping factor also. So for this we are gathering these details through the frequency waveform measurement. So let me explain you here. So what happens to the ideal waveform? What is the ideal waveform here? So if you consider a band pass filter, it goes high and remains stable and it again goes low. So there is no major fluctuations in this. This is the ideal waveform. But when we go for practical waveform, what happens? We are having a particular amount of peak overshoot and a damping factor. Okay, these things have to be considered, and we need to go through the methods for mitigating these things. Okay, so that's why we are going for frequency response. And here these are the frequencies of special interest. Okay, these are the fringes. Okay, fringe frequencies. These frequencies we need to take more measurement so that the device can be more accurate. Okay, so if you go for digital impulse based testing, the continuous signals are converted into a digitized format and we are taking the test measurements in these. Next, noise and distortion. So these for any circuit they are not free of noise and distortion. Even in digital circuits we have noise, and in analog circuits we have a lot of scopes, and we have a lot of challenges in terms of this noise and distortion. Okay, so what are the distortions that appear here? The first one is harmonic distortions. Next, intermodulation distortion and the crossover distortions. And what are the causes of these types of noises or distortion? The first thing is non-linearity of the circuit. If there is any mismatch within the circuit, we have a fundamental frequency, and from that fundamental frequency we have a lot of multiple frequencies which are multiplied by the fundamental frequency. So that is called as a harmonic. The next is saturation. When the circuit becomes saturated more than the expected time, it causes a clip, and the crossover distortion is caused due to the mismatch between the devices or the transistor within a circuit. So how will you find this? How will you characterize this noise? First thing, if you apply a sinusoidal waveform through a filter, and then you perform a Fourier transform on it. Okay, by applying Fourier transform we get the frequency domain parameter of the circuit. Okay, so the input you are giving in time domain f of t, or you consider x sine omega t. Okay, once it passes this FFT, it becomes a frequency domain signal, and by measuring this we can go for this frequency. We can measure the frequency domain properties of the particular circuit under test. Okay, here if you see here, you have a fundamental frequency, and that fundamental frequency, due to mismatch, you have many other harmonics within the circuit itself. Okay, next is intermodulation distortion. So intermodulation distortion is caused due to the clips within the circuit. So what is the summary that we have completed so far in this particular to summarize the topics that we have covered in this particular lecture is what two different types of analog test approaches are there. One is specification oriented and the second is waveform oriented testing, and I have outlined the different analog test waveforms: sine, step, triangular, chip, arbitrary and modulated signals. And we have discussed about the parameters that we need to measure for DC and AC parameter testing. Okay, so what will be the topics that will be covered in the next chapter, next lecture? We'll be covering the analog to digital conversion parts. Okay, thank you guys. Let us meet in the next lecture. Bye.